So let's proceed to sample problem number 1. So for this one, we're going to tackle about shear stress. So for this problem, we have a W18 by 50 beam with a yield stress of 345 megapascal. A support is simply supported over a span of 5 meters. The beam supports a uniformly distributed load of 12 kilonewton per meter that includes the self-weight of the beam. So for this one, it is obviously stated that we have a length of the beam which is equal to 5 meter. And siyempre, sinabi din dito kung ano yung gagamitin nating section and the given load itself, wherein it is stated also that the self-weight is already included to the given distributed load. So we have a distributed load. So let's say this is our distributed load. Okay, sorry for the drawing. So let's consider a certain beam. Okay. A simply supported one. So meron tayong naka-apply dito na 12 kilonewton per meter. So this is 12 kilonewton per meter. And the length of the simply supported beam is 5 meters. The beam is laterally braced at the supports and at the third points of the span. So, nag-place daw sila ng mga lateral supports natin sa mga supports and at the same time at third points. So, meaning to say, ito yung mga third points natin. So, yung mga points natin, yung buong length natin, dinivide siya sa tatlo. Yun yung mga third points natin. Determine the maximum shear stress and the average shear stress in the beam. So when we are talking about maximum shear stress, average shear stress, we are pertaining to the actual stress na naranasan ng beam natin upon the application of our load. So there is a difference between the allowable stress o yung design stress na tinatawag natin sa LRFD versus the maximum shear stress and the average shear stress. So by principle, when we are talking about computing the actual shear stress that was experienced by the beam, so it was given by the formula FV is equals to VQ all over IB, which was already discussed in strength of materials or the mechanics of deformable bodies. So for this one, kapag nakita natin na small f, yung denotation ng stress natin, ng shear stress natin, meaning to say, this is the actual stress. Unlike sa mga pinag-aralan natin previously, yung kinukuha natin is yung FB, kapag capital F, so meaning to say, ito yung mga allowable or design stress. So for this one, kukunin lang natin yung actual stress natin, meaning to say, magbe-base lang tayo dun sa loading natin. Unlike sa pagkuha ng allowable or design stress, ang daming nating procedures, ang daming codes na sinusunod to obtain that data. So, paano ba na-experience yung shear stress? So, let us consider this example. Let's say, magka-cut tayo ng section dito. So, mag-cut tayo ng section dito sa gitna. If we were going to cut a certain section, since it is a beam, cut tayo ng section dyan. So, meron tayo dito na na-cut na 12 kilonewton per meter. So, we cut a section. Since nag-cut tayo ng section dyan, lilitaw yung mga forces natin o yung mga internal stresses natin. So, una is the moment. and also yung mga shear natin. So, etong mga bending moment natin na to, it causes flexure kasi binebend niya etong beam natin. Ito naman sa mga vertical forces natin o yung mga shear force natin, ito naman yung nagke-create ng shear stress. So, for this one, when we are talking about shear stress, we are pertaining to parallel area. So, yung i-consider natin dito, siyempre, yung cross-section natin. Kasi yung cross-section ng beam natin, it experience bending and at the same time, yung shear stress natin. So, let's calculate for the value of our maximum shear stress muna, o yung FV is equals to VQ over IB. So, in computing for the maximum shear stress, so hanapin natin yung value ng FV max. Since maximum yung hinahanap natin, meaning to say, yung kukunin mo dapat na shear, naka-maximum din dapat yan. And at the same time, yung ko-consider mo na Q, dapat maximum din, all over yung I multiplied by B. So for this one, kunin muna natin yung value ng Vmax natin. Since we have a simply supported beam, so the value of our Vmax, that is only equal to WL over 2. Wherein we have an L, we have a W which is equal to 12, L which is equal to 5, multiplied by 2. So we will have a value of our maximum shear, which is equal to 30 kilonewton. So nakuha na natin yung value ng Vmax natin. So yung I naman natin, yung i-consider natin is the IX. Kasi nga, malakas along x-axis yung cross-section natin na W section at hamak na mas mataas yung value ng IX compared sa IY. Kasi yung IX natin, that is yung strong axis. Samantalang yung Y-axis naman, that is the weak axis naman. And yung B naman, so later i-discuss natin yung pagkuha niyan. So for this one, kunin muna natin yung value ng Q natin. In determining for the value of your Q. So, ito yung statical moment area natin with respect to the neutral axis. So, yung mga statical moment area natin, imo-moment natin sila with respect to the neutral axis. So, for us to calculate for the value of your Q, let us calculate first for the designation of your neutral axis. Since we have a W section having a depth of 457, tapos symmetrical yung top flange natin, bottom flange natin. So meaning to say, nakapagitna lang yung neutral axis natin. So for this one, this is our neutral axis. So, upon locating your neutral axis, you can now calculate for the value of your Q. So, paano natin i-compute yan? So, lahat. So, you can choose yung top o yung bottom. It depends upon your choice. So, for this one, kapag kinonsider natin yung top, no? Pag kinonsider natin yung top, we are under sa tension. So, kapag sinasinalan ka top, this is compression pala. And yung nasa baba naman is tension side. So, whether you would choose compression side or tension side, sa pagkuha ng Q, parehas lang naman yung makukuha nating Q, as discussed sa SM225. So, for this one, let us consider na lang yung top section. So, imo-moment area natin to. Moment area natin yung area na to. So, let's say, etong mga area na to. yung nasa taas muna yung imo-moment natin. So let's calculate for the value of your Q. So imo-moment lang natin yung area with respect to the neutral axis. So we have Q is equals to, so yung base niya, yung base ng flange, which is equal to 191 multiplied by the thickness of the flange na 14.5 multiplied by the moment arm, yung distance ng centroid ng section natin sa top flange with respect to the neutral axis. So yung kalahati from the neutral axis to the top flange dun sa top fiber, so yung location niyan, that is 557 divided by 2 minus, siyempre, yung so nakuha natin yung distance from the neutral axis to the top fiber of your flange minus yung centroid ng top section natin with respect dun sa top. So that is 14.5 divided by 2 plus we will going to consider yung nasa web naman. So for this one, ito naman yung i-consider nating area. Okay. So yung ano natin dito, yung height natin sa part na to, we have 457 over 2, kasi kalahati, minus 14.5. So you will have a value of 214. So for this one, we have a value of 214. Plus, so yung thickness ng web natin, which is equal to 9.02, multiplied by yung height, which is equal to 214, multiplied by, so yung centroid natin dito, so that is 214 divided by 2, yun yung distance ng centroid neto with respect to the neutral axis. So we have a value of our Q, which is equal to 819,291.835 mm to the cube. So makukuha na natin yung value ng maximum shear stress natin. So FV max, so yung Vmax natin, so yung mga ano natin dito, no, laging naka-Newton mm tayo. So, eto, para maging Newton, we will just multiply 1,000. And then, yung Q naman, we will just rewrite it. Yung I naman natin, yun yung IX. And, siyempre, yung B naman natin, yun yung dinaanan ng neutral axis natin. So, for this one, yung dinaanan lang ng neutral axis natin, yun yung 9.02. And we have a value of our FV max, which is equal to 8.18 megapascal. Next naman, yung pagkuha naman ng average shear stress. So, dun sa diagram natin, sa shear stress, so we can denote na yung halos kumukuha ng shear stress natin or nagre-resist sa shear stress natin is yung web natin. So meaning to say, the formula in computing for the average shear stress, that is yung Vmax natin all over, siyempre yung sa web natin. So for this one, kinuha na lang for simplicity purpose. So we just consider here na consider natin yung D multiplied by the thickness of the web. So for this one, yung D natin, eto yan. So etong buong to, 457 multiplied by the thickness of the web. So etong naka-shade na to, eto yung average shear stress natin. So for this one, we have the value of our Vmax, which is equal to 30,000 Newton. The value of your D is 457 mm multiplied by the thickness of the web, we have a value of 9.02. So the value of your average shear stress is now equal to 7.28 megapascal. So nakuha na natin yung dalawang values natin for FV max and FV average. So that is our answer for problem number 1.